This
subject, so I need to
conference will
really give an
now be
overview.
recorded.
Right, so what I'm going to do is to do an overview of the system. Basically, I'm looking at the Dell core system because A, they pay wages, being brutal about it, and B, it appeared to be the best one when we reviewed it on LU at the time. So what we're looking at here is it's based on integrating existing products. So all the stuff out there is proven and making it better, making the railway better, both in noise and vibration, maintenance, ride and quality. As I said, they've got a proven track history, so most of this stuff is sort of well known worldwide. Right, if I can get my computer to click in. Yeah. Right, so I'm going to whiz through the vibration side of it pretty quick because that's something that should be well known to a lot of people, and then I will go through the other bits that we tend to forget about resilience, how to sort of look at stress, how to manage between different track forms, interfacing into legacy, and the maintenance liability that we've got. This is a sort of basic overview on what we've got in the way of different types of vibration. There's primarily two types of vibration: airborne noise, which is your wheel squeal type, which is a high frequency. Resilience won't manage that to any great extent, but the big E is structural borne vibration. That tends to go through the clays or the concrete into the foundations of properties, and then the property acts as effectively a loudspeaker, and you get this low dull rumble, which since the advent of Crossrail and setting the bar really high has become a major problem within the urban area. Just some idea is the cost of it. We all know the cost of on-site issues on rail management, trying to sort of keep your alignment and rail head profile in a good condition to reduce the input factors. But the legal cost is starting to become a major issue on this. The 35 dB on that graph is probably, you can just about hear it in a basement, and as it goes up through to 55, that will be a real painful noise. The magnitude increase is vast. Obviously, the legal cost depends on the area you're working in. West End of London, that can be in the millions, whereas some of the less affluent areas, obviously the cost will be less. But it is a major problem on this, and we should start factoring this into cost into our renewals, because it does have a big effect on the global business, not just the localized maintainer. A quick review of what's out there. So direct fixation would be your standard pack track type arrangement, or a concrete in base plate. Basically doesn't give you a lot, as you would expect. Embedded rail, which is the Edelon type of system, and tram type system, will give you circa 5 dB. Does have a bit of disbenefit on airborne noise because of reflection. And then we come down to the compressive type base plates, and the sort of what would you call it, the sonical type system. You can generally get about sort of 10 dB, and then we go to the resilient Lord egg, Cologne egg type arrangement, which we have got down to about 14. And then after that, we go to the two types of floating slab track. Generally, base plated type systems, you can usually get the price about the same. So when you get a real magnitude shift in cost when you go to floating slab track, both in maintenance liability and one-off installation costs. So it's worth thinking about what you're doing there, but you've also got to align this into the system. So right, managing the resilient in the rail system. So you have a rail, obviously, and you not only want to get your noise and vibration down to reduce the input factors into your vibration modeling, but you also want to understand what it's doing to your system and ensure that we don't end up with a heavy liability of maintenance or major renewal costs at an early date. So, as an industry, we're pretty poor actually at looking at resilience. We tend to think of it as the rail only going up and down, and experience has shown the tube network has been a brutal area to try things like this, because the sharp curvature, compromised transitions, etc., do bring out faults really quickly. So you've got to look at the lateral forces, lateral movement as well. The other thing you've got to look at is a preload of the system. If you get a very soft bit of rubber and then put 14 kilonewtons on it, you've obviously lost a lot of the effect of it. So you're taking out a lot of the use of that rubber can give you. It also has a unwanted effect that we experience quite often on some systems, is where, because you put a preload on the rail, you've taken out that initial compression. So with a system like this, you end up increasing the bend radius from about 2 to 3 meters to up to 8 or 9 meters. So this means that the pads deflect incrementally depending on the load shared through the rail. If you've taken up half of that compressibility, where the bend radius ends, you end up with a pivot point, and the other side of that pivot point you get an uplift. And so this is something you've got to be very aware of. With a soft system with a high preload, you can get uplift in there, so it's something you've got to look at. And this also can be affected by the maintenance procedures or installation procedures where the bolt is over torqued. So you've got a bolt that's torqued down through the resilience system. It then effectively nullifies the resilience, but the system either side of it is relaxed, and that will act as a pivot and lift your next base plate out of the ground if you're not careful. The other one which resilience systems do suffer from is resilience fatigue in the resilience holding down system. So a bolt going through a rubber pad, you don't know what it's doing. It's going to be moving laterally because that's what it's there for. You've got to look at the fatigue cycles within that. How long will it last? How do you manage it? How do you inspect it? And how do you identify potential pre-failure modes rather than the bolt dropping off, which happens quite a lot. Secondary stiffness and deflection control, that's all about when you get fault mode within your vehicles or in your track. So you get an extreme hammer blow by a wheel flat combined with a defect on the rail. So you need to make sure that that rail stops its deflection. It won't perform at that when that secondary stiffness is hitting for your noise and vibration or vibration control, but it will stop you getting in a dangerous position. The other one is, which is linked to it, is lateral shift or rail roll. In normal track with a system, you tend to get rail roll rather than lateral shift of the rail, which is fine up to a point, but after a certain amount, you do tend to lose your wheel rail interface. So if you're looking at a system with design resilience, you like to look at it to see if you can get a full lateral shift across rather than the rail rolling. So a millimeter of lateral shift in a rail roll changes your angle of your rail, whereas if you've got a lateral shift, you still maintain your rail profile. The other thing is you've got to assess how your rail deflects. Are you going to increase the propagation of them? Are you going to slow them down? If you've got very soft track, but it's laterally very stiff, you tend to get accelerated corrugation, and any defects that do occur do happen quickly. So you've got to look at managing it. I'll go into individual bits a bit deeper when I go through. The next slide is a classic, which we've probably all seen, anybody who's worked with slab track. In this one in particular, I think it's in Germany, they had a 15mm pad in between there. It's literally destroyed the pad. The bolts, you can obviously see, are completely under fatigue and the concrete's broken. And the other mode we get quite often is that the clip will fail because you're overstressing the clip. So this is what I was saying about the fatigue points going through there and making sure you manage your lateral resilience. Unfortunately, being fatigue cycle, it all tends to happen at the same time. So we don't just get a one-off break, we tend to get what we call an unzipping effect. I missed that one, sorry. This is the original sort of Cologne egg style system. It's a twin part bonded rubber, so the Rubber is designed for the rolling stock or the environment you're working in, so you change the stiffness. The whole thing can be tailored, so the angle of the interface is changed depending on what your requirements are. The system on top, whether you want a Pandrol system, a Voslo system, or whatever, can be changed. These are excellent. They've been in track for 40 years in Cologne. They're changing them now because of line upgrade, not because they're worn out. Problem with them in the UK is that they don't meet the Euro norms, not because they're not fit for purpose, but purely because they're so soft. The Euro norms don't cover in that area. So we've accepted it. Well, when I was on the London Underground, we accepted it on the Underground. They're performing really well. We based our trials on the old DIN method, so the German standard, which is Zinnen and Theory, and plunked on a 200-meter radius curve, and it's performing really well. But it's sort of the next stage up, really, so that the Dell cores can meet the requirement is a pure compression plate. Again, it's a two-part system, so you've got the top metal plate and the bottom outer ring of metal, and then you've got the rubber that is bonded to it, chemically bonded to it in the same process that you do bridge bearings. You don't get quite as good vibration attenuation on it because it's a compression plate rather than working in shear, but it's pretty good because you've got no preload on it. It's a captive type arrangement, so in the very rare event that something does go wrong, which I've never heard of, it won't pop out of its system because you've got the ears that curl over the top. It's as far as the track guys are concerned, it is basically a base plate. There is nothing else in it. There's nothing else to do to it. It's just screw down and go for it. It's in Australia where they first produced this one. It's been in service on, I think it's 40 million ton per annum, 35 ton axle load, no issues. So it's got very low cost. It's the Americans are using it as well. They put it on their test track and can't break it either, which is quite good. The stiffness goes down to about 16, but that's stock dependent. It's very obviously because there is no metal work going through the rubber. It's very good for isolation of electricity. Within the design in the UK, we have provided a lateral adjustment, which DLR are currently using to tighten their gauge up where they've got existing track that's fatigued and got wide gauge. They're resetting it at wide gauge. Then after they've finished a section, they run it back to design. You can shim this one up to 25 mil. My preference is you only use that for maintenance, but some of the operators do tend to use it as a norm. I've gone over most of this, but I just revised no fatigue point, which is one thing. Again, this is dual resilience, so once you get to a certain point, the rubber won't compress any further. That's both laterally and vertically, so it just goes solid. Again, it won't affect the plate. If you run a 35 ton axle load over it, it just doesn't operate to its performance criteria. We reduce peak loading by the load share. As I said earlier about the bend radius, you can actually get the loadings down to about 40% over the wheel. It's natural rubber, so it gets stiffer with age. So although the performance will degrade in time, you're normally looking at getting 40 years plus out of it. It stiffens, so there's no safety risk in it going too floppy. The whole system was designed using existing tooling, so we keep the same maintenance process and reduce the intervals because we've got the reduced stresses. It's 40 years in places. DLR, we took some out, did some testing on them. I think they've been in about 32 years around Canary Wharf, and I think the degradation was about 4%. We allow 10%, so yeah, there's massive life still left in those, so they're still going well. Enemy performance, we can tailor it. Obviously, dedicated stock, it's very good. When you get mixed traffic, you've got to compromise a bit, but we can still get a very good performance. And it's very compact and ideal for constrained railways. In fact, with LU, we couldn't actually fit anything else in. This is a slide. I won't go through it in detail because it's a bit heavy on the eye. It's a good one to go through. It's a good one to go through afterwards. You've got the checklist, which is your input parameters up in the top. So you put all your track details and vehicle data in. The calculation results will give you that deflection curve. This particular one was done to fault mode criteria to work out the worst case scenario. So that is worst case scenario. So don't take that as a given that you're going to get 2.5 millimeters deflection. You're not. You're going to get sort of probably about 1.5 mils, which is perfectly acceptable under a bend radius of 5 or 6 meters. No problems. This is a relatively soft one, 13 kilonewtons per millimeter. So if you look on the line from the side coming down there, nominally 63 is the frequency of 63, which is 47 on that, is giving you an absolute insertion loss of 10. So it's pretty good. It's up there with the best of them. But again, I'm not going to go in details, otherwise I'll bore you to tears. As I was saying about the bend radius, so this is what you see under a base plate. This is indicative. It will change obviously with how you do it, with load and stiffness, but you know, it's not unusual to get well below 50% by increasing your bend radius. Normally in a base plated system with a conventional EVA pad, you'd be looking about 75–80% on one, and then the residual going between the two. On some of the softer systems, we can go out to about sort of 6 plates either side of it by utilizing that, which shows that you can get your fatigue loading right down, which is what one of the aims we need to do, is to keep that fatigue loading low so that we increase the life of our asset. I did cheat on this one and just copy it in. So what you've got is the vertical forces. They go through the top plate into the rubber. Because the rubber is resting on the concrete base or whatever your formation is, you create a really high friction on that concrete, and that holds all your lateral forces. So we've reduced the lateral forces, plus by pummeling that rubber down on top of the concrete, we're actually holding most of our lateral forces from going through the bottom plate. So we are keeping the fatigue out of there. We did some FEA, and on the central line we modeled Caxton curve, which is a 60-meter radius curve, and I'm trying to think what speed it was, but I can't remember. But what we found was these are on this 60-meter radius curve with central line stock, which is horrible for track. We actually still found that the preload from the bolts was causing more stresses than the train going over it. So you know, that was sort of very reassuring, compared with the legacy system where we was getting something like sort of 100 kilonewton going down in the system, and effectively sort of the whole bolts were under fatigue straight away. The rail fastening system, whatever you have on top, it actually gets a lot less stress because you're not rolling the rail over, you're laterally shifting it in a rubber. So you'll find that whether it's a bullet system, Pandroll or Voslo, you won't get any faults in there. They would last for donkey's years. With the lateral movement, obviously, it's going across, you maintain your railhead profile a lot better. As I said before, you tend to find on this system, it's a very big subject to go into, but I will just touch on it because you're damping everything out. The railhead damage generally is reduced. There are certain conditions if you mix up natural frequencies, which will happen with any track form, where you can get problems. But again, that comes down to something which, as a system, we need to look at and assess that beforehand. Sometimes you're led into it and you just can't avoid it. But it's unusual, and it's only happened to me once on the central line, and that was due to conditions. But again, there are ways that we can play with that in the longer term. The other thing coming from resilient systems is, you want to manage your stiffness back out again. There's no point putting a lovely new system in that manages all your stiffnesses, and you get back to your traditional system and you go wallop straight back in, and move your maintenance liability from one area to another. This was done in Australia, I think it was in the 90s, hence the PPE is a bit more lax than we would see nowadays. So you can see what they've got there. They're running out the Dell cores off the bridge and then into the PNC sleepers, which have different stiffnesses of rubber to slowly manage the stiffness back out. This is what we designed on LU. The LU design section came up with this, and so what we've got here is a selection. We come off the track form with the 22 kilonewtons, and then you have a section of 22 kilonewtons on very wide concrete sleepers that then go into 32 kilonewtons and then run it out through. The idea is that we use a bend radius to change the stiffness, so we don't have to change every single base plate. We can use the rail to assist us in that. As it goes through, we get a slightly different stiffness as it runs through, and we can run it through and keep our rate of change of deflection down to a minimum. One thing which we have to remember is that it's speed related. So the faster you go, the more you got to put in there because it's rate of change per second. The advantage of these stiffness transition is that they are, there's no intrusive works. You bring it all on site as you would as a panel, dump it in there. We tend to put a few geo cells in there for belt and braces, but basically we're not gonna rip out, have major concrete structures under there. It's all up and above the sleeper is that's the bit that's moving, so that's where we keep it out of the way. We've got a wide sleeper, so that helps as well. And the other thing is that there is a great love of changing the stiffness on a slab track, where it does seem a bit naive to me that you spend all that money working out what's the optimum for your slab track, and then the most critical bit is the end, and then you start playing with the stiffness on the end. So I always prefer to run it out and then change it back into an area outside of that, in the ballasted area, where you've got a bit more control, especially if you've got noise and vibration, because you stiffen it up on the end, and that then just livens the whole slab up. So yeah, the dual resilience also manages the lateral deflection. One thing you've got to remember, when you come off a resilient track form, your track not only goes up and down, it goes side to side. So if you then lock it laterally, what happens is the sleeper will roll very slightly side to side. That roll will then roll on the ballast, and that ballast will take the cohesive bonding off the edges on the interface between the sleeper and the ballast, which is the one area you want to maintain, and that's where the failures normally occur. So again, it's thinking about that deflection as a global circle rather than just up and down. And also, if there is a change in the stock movements where you need to change the stiffness, it's relatively easy to do. You just unbolt the base plates and off you go. Here are two that we've done on two different networks. The dark fadey picture is on the Metline. I think that's been about 5 years. As far as I'm aware, I did ask the other day, no issues. The other one, which is obviously a lot longer, is on near Canterbury, River Stour. That was put in May. We did some vibration testing the other day, and it's performing well. So they're the two types we do: main on operator, mixed traffic, and dedicated LU stock, S-stock. The other area of fixed track forms that we sort of is coming to a freight at the moment, where we're changing from softwood stroke hardwoods to FFU, or hopefully at some time move away from FFU to concretes and steel. This particular picture is Sydney Harbour Bridge. It was done in the 90s. Again, it's just up for replacement because the timber underneath it was failing, not the system on top of it, and it's a line system upgrade. So at the same time, they're changing the base plates. Historically, we always used to have marine softwood, brilliant timber. Used to last for donkey's years, and it was also quite flexible. With the demise of good quality softwood, we moved to hardwood, and latterly to a plastic composite or FFUs. This is Network Rail, using extremely stiff, completely different sort of way it reacts with the chair screw. And they do suffer from, when you have peak forces, the screws do tend to fail, or if in hardwood, the top surface of the timber starts to fail and the holes go oval. I think anybody who's worked with long timber bridges will know they have their own anomalies and history of failures, etc. And the peak forces do tend to overcome the friction between the base plate and cause screw failures, etc. So by using resilience, especially with the lateral resilience, we do load shear laterally as well as vertically, so we can actually reduce the forces going in. And again, as I said before, the vertical forces do actually compress straight into the timber stroke composite, creating high friction and therefore reducing the force in the screw. We do get, and again, I'm a great advocate in looking at replacing timbers for steel or concrete to get a structural form. It tends to be awkward because it's a multidiscipline design, because it brings the civils guys into it. So I know it's been done with the Viper system, and I think that's working pretty well on a few of the bridges. I haven't heard any major issues, but I think with the cost of FFU and the lead times, etc., I am seeing projects that are coming on for FFU are being replaced with timber because they can't get the FFU, and we end up with a bit of a compromise design solution at the end of it. The use of resilience in conjunction with stiffness transition does give you an enhanced solution. It's usually get a better cost out of it as well. And also we're looking at keeping your maintenance liability down to a way. This is really going off piste a bit of sort of stuff we did with LU, but I was just going to sort of talk about it. With the check sleeper arrangement that's happening, obviously since we've gone away from bullhead, we've ended up with the very good system we got now, but it does suffer from issues of fastening systems to the concrete or the timber because of its stiffness. One of the things we looked at within LU was to provide a resilient system on a concrete sleeper so that we could again use that bend radius to reduce the peak loading in the system. This was our first sort of trial effort, which worked well. I think it went in about 7 or 8 years ago. As far as I'm aware, apart from its follow-up tamp, it hasn't shifted. We've also used this in my days in LU on the deep tube. I think the tightest radius we got down to is 90-meter radius curve. Every site was handed back with very little defects, which was always the case before when we handed back, that the maintainer wouldn't accept it. To my knowledge, because nobody's moaned at me yet, they're all performing well with no issues. If there are problems, please somebody get in touch with me. But what we did here, we integrated the Schwiag top plate, and I worked with Schwiag and Pandrol to get this design, and then integrated it into the Dell core base. So we kept the known system of the Schwieg. We balanced up the loads between the Schwieg clip and the Pandrol clip to get an equal toe load, and then put it on a Dell egg type system. There's quite a lot of these on the system now, and it's actually one of the few plates that's made in the UK, resilient plates that's made in the UK now is a Czech one, so that's quite a novelty nowadays. We're looking to increase the asset life on this from nominally sort of you would expect half life out of a check curve compared with the plain line curve. So we're looking to increase that asset life, hopefully double it, reduce railhead damage or the speed it appears, load share between sleepers. So that means that laterally we can hold our alignment a lot better. We're using the big sleepers again, so with the reduced loading and the big sleeper, ballast should get a hell of a lot more life out of it. With the obviously the degradation of the geometry being slower, derailment risks are reduced significantly. Maintenance is maintained as we do now. The need for lateral end plates and things like that are reduced because you've got the load share, so you're not peak loading the ballast. The installation methodology is unchanged. It's just a heavier sleeper, which means you need a bigger digger or you lift less sleepers at a time. It does frighten off project managers, but we found actually it was easier to install the conventional system. And we also build in an allowance for flangeway gap and track gauge changes requirements for different systems. So the upstand on the check is allowed to be milled to a certain amount, so we can optimize the flangeway gap to the system on the railway. There's also quite a lot of P&C work that's been done worldwide in the same system on slab tracks. The picture in the bottom corner is, I think that's MTR somewhere with a massive great scissors crossover. There's 4 or 5 of these been put in on London Underground. They work well. The only issue we get is around the POE, making sure that the signals, points motors and that can fit, and managing the resilience and the movement between the points motor and the track form. The difficulty we have with signals is they can't understand that the movement you get is the worst movement you ever will see, because they're used to it being fixed and then slowly degrading. Whereas with a resilient track form, you are going to get the highest movement at the start, unless something goes drastically wrong, which generally means that the least of your problems is the point motor not working, and it's probably benefit if it does fail and stops traffic. But you know, it's a non-issue. But we are struggling a bit with that, and I think we probably have to go to some more novel solutions in time to come. But in the constraints of the deep tube, it was getting very difficult. These are a few odds and sods we did as well with Schwieg. We molded in 2 types of slide chair. One is a conventional slide chair and the other one is a slide chair with a roller in it. So they are Dell core system integrated with the Schwieg system, which is great fun working with people, with other engineers in other sectors. The other thing we interface with is the Edelon crossing. So it's a complex arrangement, but the Edelon products are supplied by the James Walker Group, which is also part of the supply chain for Dell core. So I got dragged in by the overarching company to work out a systems design, because what they were finding is they were putting in the Edelon level crossings, but moving the maintenance liability from level crossing to the transitions. So we worked out by using the transitions you've already seen that we could then actually reduce the maintenance liability and keep the liability of the transitions down to the same as that of the plain line around it. So it worked really well. Here's a picture of the first test site we did on a heritage railway down in Kent, East Sussex. So it's not far from you guys. You can have a wander down there, have a look at it. We've got short transitions. You can see the green transition to the stiffer ones. So that's the way we identify the two different stiffnesses. The big sleepers in there, the ends are capped off because it's for resin that's poured in there, and those just get knocked off once the resin's set, which normally takes about an hour. That crossing's been in, I think it's 4 years. It probably needs a tickle up on the transitions to take a bit of the sort of bit of the slack out that's happened over the year, because it was never followed up tamp. But I was out there about a year ago, and it looks good as gold. Trucks running over it at 60-70 miles an hour, and nothing's moving. Right, well, that's a quick fly through. I apologise for the speed it went through. There's a lot of subjects here, and I'm more than happy to sort of take some of these subjects, either go in depth with you guys depending on what you want to hear, or do a version 2 of it and go into more detail and look at more projects. So really, it's just sort of over to you guys and say, you know, are there any questions, anything you'd like to talk about? Obviously, I've got my details on the slides, so if you want to go offline, you can just give us a call sometime and we can discuss whatever.
Peter, thank you for an excellent presentation, very informative. Thank you for sharing that with us. If anyone has got any questions, you can either unmute yourself and raise them, or if you're not feeling that brave, just populate in the chat and I can read them out to Peter. Just thinking about Peter, I've got a question for you. With regard to the Dell core plates, the actual fastening of these down, is that something that you guys would get involved with? And if so, is it a bolt that's glued in, or is it a sleeve, like a Voslo sleeve, that's cast in? What sort of, how would you respond to that? What sort of feedback can you give us?
Basically, again, that comes down to what the client requires. We tend to recommend a system like the Voslo system that's used on PNC. Yeah, on East London line, we're looking at the moment for a bolted system. It's really the client's requirement, and we discuss this at the concept stage, and you know, we can do whatever the client needs. We've obviously got our views of what we prefer, and yeah, we sort of, once we've offered something, we will say that system will work, but we won't guarantee how it's fitted to the concrete. We'll advise, but then that's up to the operator to get somebody else to do that design.
Okay. And is casting in an anchor an option, or would it always be glued in?
Again, top-down construction is not unusual. We do top-down construction or bottom-up. It's, yeah, provided we can get the torque on the bolt, yeah, that's all that matters. So yeah, the construction is something that you would work with somebody like myself, which I've done with DLR and with Network Rail, and we work through the best system to fit how the operating practices are on that railway.
Okay, good stuff. Thank you, Peter. Has anyone else got any questions for Peter?
Yeah, I've got a question. It's Phil Edwards, Peter. Hi.
Hi, Phil.
How you doing? Yeah, speeds. I just I didn't. Maybe I missed it. I just wondered what the highest speeds that there are examples out there where this product has been used. Because quite clearly there's a lot of sort of low speed and metro type applications, but what about the sort of higher speed end? Anything that you can say about that at all?
Basically, at the moment, we've only tested to Cat C, which is 125. It's running at over 100 mile an hour on MTR, but normally I think the benefits once you get over that 120 mile an hour mark are probably, you know, the dynamic effect of the train is such that you'd probably not go much above that, but up to 125, it's got a good performance.
Yeah. And do you think that's because pushing, you know, up through the speed range that you would have problems on the lateral forces because there's some give there at the higher speeds on curve track? That might be an issue, do you think? Or maybe
Well,
it's just simply that you haven't had the clients with the railways at the high end come to you. I don't know. Is that something you're looking at testing or?
well, the thing about it is that it's market viability. Once you get above 125 mile an hour, people don't like bolts in railways. They like to avoid as much as possible as many fixtures and fittings as they can. Obviously, we've got quite a few bolts in our railway, even though they're known and understood. So it tends to be, you know, one of the prerequisites that's come out of a lot of high-speed lines is that they want a casting situation. So that's really ruled us out at the early stages. I'm sure, yeah, the other thing we've got to be careful of is natural resilience, making sure the natural frequencies don't clash in the system because of what we are, which is manageable, it's designable. But it's really, yeah, market forces have dictated that the system we use doesn't meet that criteria purely due to the holding down system.
Yeah. Okay. Okay. All right. Thanks very much for that. Anyway. Yeah.
Does anyone else have any other questions for Peter while we have him with us? If not, hold your peace.
Hello, Peter. Thank you very much for an excellent presentation, Peter. I think that we don't really take it too much in and doing enough work on it, on the resistance, on the track and that. Just recently I was involved in a tiny little one, and it's so much to take in, and it's probably a shame that we haven't got many more test houses and test tracks that we could try it on. But thank you very much for excellent presentation. We know if we got it wrong, it is a very job to put it right again afterwards. So thank you once again. Thank you.
Thanks for inviting me along, Howard. It's nice to talk to you guys.
So yeah,
thank you very much.
Yeah, so thanks, Howard, for doing the vote of thanks. Appreciate that. Thank you, Peter, for an excellent presentation. And also thank you to our guests from Wessex and from Croydon. Thank you for that. Hopefully you enjoyed yourself. And if you ever want to attend any of our other meetings, of course, you are most welcome. And with that in mind, just a gentle reminder, our next meeting, once again, will be virtual. Will be on Tuesday, the 9th of November. And it will be David Packer presenting his paper on the engineering of the Romney Hythe and Dymchurch Railway. So it promises to be another excellent presentation. So thank you to all. Have a great afternoon, evening, and I'll speak to you all soon.
Lovely.